Hi, everybody. Welcome to the UW Robotics Colloquium. My name is Dieter Fox, and it's my real great pleasure to introduce today's speaker, Julie Shah. Julie is a faculty at MIT in the Aeroastro department. She's doing work in the broad area of human-robot interaction. Before joining the faculty, she spent a while also at Boeing Research, where she looked at applications of robotics in aerospace manufacturing. So she has some real industrial experience, which of course is always good to drive some of the, I think, academic research that's going on. Her specialty is really in developing techniques for fluid human-robot teamwork, especially in, let's say, task-specific domains such as manufacturing, surgery, or even also she's looked at applications in space exploration. And more recently, not only human-robot teamwork, but also investigating human-human teamworks, how teams work together in the health domain. And for that whole work, she's really looking at the complete stack of the different kind of areas that are involved here. So she is building real robotic systems and developing these. She's also looking, of course, at many of the techniques from the human-robot interaction community, but also I think a lot of her work is inspired by and also develops new techniques in AI reasoning. They are also, for example, even looking at things like human activity recognition, modeling of human behavior in general. So, and not surprisingly, of course, she received various awards for her excellent research, among the MIT TR35 award, and also various best paper awards and an RSS Spotlight award. And with that, I'm super happy to hand over to Julie, and we're all excited to have you.
Thank you so much. Thank you so much for having me. I'm sorry to not be able to visit in person. I really enjoyed the time I spent living in Seattle many years ago, and then my visit out to you a number of years ago as well. And so I look for opportunities in the future to see you in person. But this is good in the meanwhile. So I'm delighted to share with you a little bit about my work, my lab's work over the past few years. And so we work on developing, so I'm an AI researcher and a roboticist, as Dieter mentioned. And I work on developing intelligent machines that model people to be able to collaborate with people as easily and naturally as humans work with other humans. And the greater vision behind my lab's work is to develop AI, robotics, and more broadly computing that augments human capability rather than displaces or replaces us. And I've worked for many years in robotics for manufacturing, developing robots that deploy and work alongside people, for example, to build planes and build cars. And in many industrial settings or warehousing settings, we do have these really excellent examples of human-machine collaboration through careful design. So as many of you are aware, Kiva, Amazon Robotics, is really excellent example of decomposing the work of humans and robots. But in many of these installations, these systems are still operating in spaces that are largely physically separate from people. So that's one way. And in automotive manufacturing, we have collaborative robots, cobots, that are now being deployed outside of cages, right next to people. This provides a benefit in terms of more flexible use of the factory footprint. And so they're safe enough to be really right alongside next to a person, as you see in the picture. But they're not working interdependently. And so these systems, I say they're really systems that coexist rather than collaborate. And this is okay. There's a lot of benefit we can realize through these approaches. But I do want to maybe let's just do a stat and see, talk about where the trends are going. There's something like 1.7, 1.8 million industrial robots in operation around the world today, and that's a lot of robots. I think it's the same as approximately like the human population of Boston, Pittsburgh, and San Francisco. I should switch out Seattle for one of those. I think it still works. But in contrast, actually, there's something like 30 million robots just in U.S. homes today. So that's a lot of robots. And I think we don't often think about there being that many robots in our homes. And that's not even counting, the sidewalk delivery robots, security guard robots, robots in hospitals and in other workplaces. Not counting these strange, like googly-eyed robots in many of our grocery stores that go up and down the aisles and look for spills. And so they don't really make an impression on our public consciousness. And that's in large part because they're still very limited in terms of the tasks that they're doing, operating in structured environments and essentially under constant human oversight. So the value that they're providing us is limited as well. And these systems, if they see us at all, we are obstacles to them. We're not humans to them, and that's a barrier to enabling them to work interdependently with people. And so, all of this is okay for now, as long as there's relatively few numbers of them. But as there are increasing numbers, this causes a problem. So one Roomba in your house that bumps into your ankle occasionally is really no problem. But when it becomes dozens of robots that you intersect with, through your apartment building, on your streets, on your sidewalks, and in your workplace, the scale becomes an issue. And this is a headline, it must be from 2 or 3 years ago now, but there was a point in time in which there were actually so many startups testing sidewalk delivery robots in San Francisco that the people in the community, the elderly and people with disabilities, actually went to the city and raised their concern that they felt unsafe on the sidewalks. And as a result, these systems were removed from the most populated areas of the city and relegated to an industrial sector with no people. And ultimately, there was regulation placed on the number that could be operating on any sidewalk block at any point in time. And so this is the sort of canary in the coal mine of systems that don't see us as people, don't model us as people, and are not able to integrate into our social environments and in our work environments in a more effective fashion. And I think it's a threat to the successful use of these technologies if we're cut off from maturing and developing them as they need to move and work among people to improve. And so, much of my lab's work is around making robots that see us as people and are able to integrate more effectively into human environments and human workflows. And so I'll talk a lot about manufacturing and the work that we do in other settings in healthcare and DoD, but all of this is enabling technology to an important technology for these new systems that are coming our way. And so I mentioned I've worked for many years in robotics for manufacturing, and this is just a really fascinating context in which to study what makes for effective human teamwork and human robot teamwork. And my dream in this work is to be able to take a group of people, for example, that are assembling a car, and be able to take out one of those people and deploy a robot to work interdependently with people and support and enhance the human work that's being done. So what does it take to make a robot that type of effective team member? And so this is where I would typically summarize decades of research in human team coordination by showing a picture of Tom Brady, but I've now taken that out of the presentation. So instead, just imagine your favorite team, so what does it mean to be an outstanding team leader? You need to know what your partner is thinking. You need to be able to anticipate what they're going to do. And then you need to be able to make fast changes as circumstances unfold and as disruptions arise. And so my lab works on developing that capability for robots and for AI decision support. And we work on developing these capabilities in 3 steps or 3 phases. So supporting the ability of humans and robots or humans and machines to come to a common understanding of the plan for how you're going to work together, which is critically important to any teamwork. But we all know that when we plan, even an emergency response team, working out their plan across a conference table, they're not going to elaborate everything that happens. And we rely on the fact that we're able to refine our plans and elaborate them through experience, through practice, and through, for example, like on-the-job training, apprenticeship. And so we also develop techniques for being able to learn from human observation, human demonstration, and through co-training, through the process of a person interacting and working with machines. And then finally, as Dieter mentioned, you can have your refined plan for how it is the system needs to integrate in the human team or work with the human. But then it's a different thing to take that game plan and then like go out on the field and play the game. And for that, you need a whole other set of techniques. You need to be able to monitor progress through the plan. You need to be able to predict what will happen with partial information, partial trajectories of what the other agents are doing. And then you need to be able to make fast adjustments. You need to be able to resequence, reschedule, adjust the timing of your activities, and replan. And so I'll highlight a bit about our work recently in the refine and then the execute area. And so, jumping into refine, I want to motivate our most recent work by work that's a few years old now, but it gives me an excuse to include the movie, which is a system that we developed to be able to learn the decision-making heuristics of this woman here who's a resource nurse or a nurse manager on a hospital labor and delivery floor in Boston. And so my home department is AeroAstro, and I really love, developing these systems for time-critical, safety-critical applications. And in learning about the job that this person does, so this nurse manager, she actually does the job of an air traffic controller. So it's her job to be responsible for taking in all of the information about current patient status across those LCD screens and the current census and state of the women in labor on the labor floor, as is captured by the handwritten whiteboard over to the right. And she makes a number of decisions, task assignment and scheduling decisions. So she decides like which patients are assigned to which rooms, which nurses are assigned to which patients. She controls aspects of the OR schedule and many other decisions. And it turns out when you work out the job she's doing, it's actually computationally more complex than that of an actual air traffic controller. And she does it with literally no decision support. And so this is a job that, much like air traffic controllers, say, an air traffic controller will tell you they're born to be an air traffic controller. It's a very, very select group of people that are selected and are even capable of performing that job. It's the same thing for these nurses. So they train for years and in some cases decades to do this job. And some can do it and some can't. And so there's no formal training process. There's no rule book for how they do this job. They really learn through apprenticeship and through experience. And so the goal in this project was to be able to learn from demonstration or observation the rules, the task assignment and scheduling heuristics that are being employed by these nurses. And much like in much of the work in our lab, we take inspiration and design structured computational models based on some insight for how people are able to do this job reasonably well. And so that was the case in this work too. But rather than going deeper into this work, which is the work of Matthew Gombley, who's an outstanding assistant professor at Georgia Tech now, I just want to point out like what it took to do this work. So the technique that we developed was very successful in learning decision-making policies of these nurses, as well as in another context in a DoD setting with military operators. But what it took to do this was, as many of you will know that develop these models, it took like my most outstanding PhD student, they're all amazing, but among my most outstanding PhD students, an entire year of embedding on the labor floor, shadowing the nurses and doctors, and identifying, as a starting point, the full feature set that they're using in their decision-making process. So given that feature set, we were able to produce very nice results and learn their decision-making strategy. But obviously, it's unreasonable to ask a person to elicit from a person the full set of features that they're using in their decision making and in every context. And it's enormously time intensive to pair a PhD in machine learning and AI to do this job. It's also not scalable. And there are things that you still miss. So one of the outcomes of this project was actually, we found on the end of it that there actually appeared to be changes in the nurse's decision-making strategy depending on the busyness of the labor floor. So that spawned a whole set of research from our clinical collaborators, published results on how nurse decision-making strategy changes, and actually C-section rates change based on the busyness of the labor floor. They have very good reasons to justify that. So C-section takes 30 minutes, it's very predictable. Labor takes, a stochastic amount of time, it's less predictable. So when things are busy, there's rational reasons why you might see more C-sections. This spawned a line of research in our lab of trying to break free from this assumption and be able to learn the latent factors that appear to be affecting an agent's decision making. So given we will be able to encode upfront a partial set of factors, how can we infer the latent set of factors? And so before I move on to talk about that, I'll give you a sense of what this system looked like. We were able to successfully deploy it in this environment, and we used it to provide decision support to nurses and doctors. Ultimately, our collaborators took this project and further developed it to be a training tool for novice nurses to be able to train up and perform closer to a level of a more experienced nurse. So it became a way of codifying the implicit knowledge of this nurse, given you had the full set of features that affected their decision making.
What is a good decision?
Right, like, and it kind of made me like, I recommend placing a schedule cesarean section patient 3 more times. Nurse Meredith can take care of her.
What is a good decision?
I recommend placing new patients in triage bed 5.
What is a bad decision?
A bad decision would be to place a scheduled cesarean section patient in room 14 and have Nurse Kristen take care of her.
Ginger, what's a good decision?
I recommend placing a scheduled section patient in room 10. Nurse Meredith can take care of her.
I don't know if you plan to go back or what, but for me it was like this one.
Ginger, what's a bad decision?
We don't know.
A bad decision would be to place a scheduled cesarean section patient in room 8 and have Nurse Meredith take care of her.
I agree.
Okay, so that's what the system looked like. So as I mentioned, this inspired a line of research where we aim to be able to move towards learning the implicit factors that affect an agent or a human's behavior. And so we designed a structured model to be able to support this inference. And it's structured in a very particular way to support efficient inference, which is that if you note here the structure, what this translates to is that when we take actions, when our human or our nurse takes actions, the state of the world is evolved by those actions. But the latent decision factors that a person holds will not suddenly change the observable state of the world. So what might latent factors be? It might be relative workload. It might be, for example, on the hospital floor, the busyness of the labor floor. It might be my own personal priority or preference for the sequence I'd like to move through the work. It might be a fatigue level that will change my performance or my behavior. And so these latent factors were really representing as human cognitive states, and a change in your cognitive state in this case will not suddenly sort of change where the objects are on a table as you're making sandwiches. And so that's the sort of structure here that ultimately supports efficient inference. Now, the challenge is that we can't learn human cognitive states or these mental states just from observation alone. And there's multiple sort of quote unquote potential explanations for a human's behavior. And to give you a simple example of this, I live in Boston, but I'm originally from New York. Both places have subways, and the behavior of the subway is observed. We observe it. It looks the same. The system goes to the end of the line, turns around, comes back, goes to the end of the line, turns around, and comes back. But the mental model I hold of the behavior of that subway is different, whether I'm from Boston or whether I'm from New York. In New York, we say the subway goes uptown and downtown, and the switching point is at the end of the line. But in Boston, we have this arbitrary station, Park Street, and our conception of the behavior of the subway is based on that station. So as I'm moving towards Park Street, I'm going inbound, and as I pass through Park Street, I'm going outbound. So it's two states that I hold, to describe the behavior of this system. But it's different whether I'm from New York or from Boston. And there's no way to really recover that based on just observation of the motion of the subway up and down the line. So we developed an approach that is able to learn or infer the latent states as well as their dynamics. And reduces the reliance on labeled data in order to be able to do this. In many cases, labeled data may be very expensive or just plain, not possible to collect. And so the idea here is to leverage high-level input or expertise by a human decision maker and things that are very easy for humans to provide. So I can typically very easily provide partial information about the policies, like partial rules of the road in one city, although I might not be able to elaborate all the particular nuances of left turns at signals and such, or partial dynamics, in particular change points. So I can tell you very easily, even without giving the names of inbound, outbound, that my conception of the behavior of that subway changes at Park Street. So that's a change point. Or in New York, the change point is at the end of the line. And what we do is we incorporate this high-level expertise or input from the expert as constraints on a variational inference process, which we term constrained variational inference. And so the idea is to sort of shape the prior over this space to be able to infer a latent state and its dynamics in a way that aligns more closely to a human-held model. And the ideal outcome of this approach is that we're able to learn the ground truth latent factors and their dynamics more efficiently than we could with only supervised data, and in a way that better aligns with that human mental model or that ground truth model than if we were using a fully unsupervised approach. And so we tested this in a number of domains, one in which a person is preparing sandwiches in some particular order of their choosing at a table, where that latent decision factor is their intent regarding which sandwich they're going to make next, and the sequence. And then you can see, a very simple synthetic environment is a little subway example denoted by the A through E, or a lane changing example for a car. And what we were able to see was that by taking this approach, constrained variational inference, we're able to much more closely align that learned model in simulated environments where we have the ground truth of that latent state and its dynamics. Much better with our hybrid approach than with an unsupervised model, and comparably to an approach in which we have a fully supervised data set that we're using for learning. And we see similar trends in live experiments with real people, where we need to look at the Hamming distance rather than the weighted KL divergence, because obviously we don't have access to the ground truth. But in comparing the action sequences, we see the same trend, so much better alignment. And so this is some recent work in aiming to learn a model of the human and their latent factors or their latent states through high-level input from a domain expert that's relatively easy to provide. And I'll highlight a little bit of work, recent work in aiming to do the same for the task model. So how can we relatively efficiently learn from observation what we want to accomplish in the task? And then at the end of the talk, I'll bring it together and present recent work in which we synthesize a task model and a human model to develop a robot policy to work with have a real robot work with a live human. Okay, so next we want to be able to learn a task, again, from relatively little data or relatively little observation. And, rather than, imitation learning or cloning, we observed that in many cases, in particular, motivated by the hospital example, in many cases, you can figure out, what is the right way to do a task, or what is the delineation between acceptable versus unacceptable behavior, even if you can't actually do the task yourself. So a medical student will shadow a doctor to learn how, to learn the flow of a hospital floor. But they may not be able to do all of the tasks that the doctor or the surgeon does. Nonetheless, after a few days, they understand what's acceptable behavior, what's needed in that environment, and then are able to jump in and pitch in as they need to. So I'm giving you a toy example here, but it's not so toy actually. So imagine a ground vehicle moving through, conducting some task. And we have two types of points of interest in the environment, the green circles and the red circles. And so this is a ground vehicle following the blue path. If I give you these 4 examples here, and look here, okay, it skips the first green, it skips the second green, goes to the third, fourth, and so on. With just these 4 examples, you're probably able to tell me the specifications for correct completion of this task, which is that the ground vehicle moves through 4 green points of interest in a particular order, 1, 2, 3, 4, but it skips one of them if it happens to be in a red no-go region. And so we as humans are able to do this. And so we desire for a robot to be able to do this too, to be able to capture this notion of acceptability. In this particular case, we're interested in the temporal specifications for completion of a task. And in this case, we'll look at LTL as the particular specification language. And so temporal logics, in particular LTL, are a very useful thing to try to infer from demonstration, because once we have that, there's a lot we can do with it. We can synthesize verifiable controllers. We can use it as a part of a reward signal and reinforcement learning. And it can also serve as a model for execution monitoring. So the challenge is that LTL, even just LTL, poses a significant challenge in terms of inference. It comes with a very large hypothesis space. And so, the key insight in this is that, we as people actually tend to use a subset of temporal behaviors, both in building and understanding system behavior, including software systems. And so what we can do is define prior and likelihood distribution over smaller, but relevant parts of this space based on what we know from the literature in cognitive science. And so we take a smaller part of this space where we're aiming to infer across a few templates. So one is global satisfaction of propositions. And our simple example, that's always stay outside the threat avoidance zone of some subset of the threats. Then we want conditionals, for example, to be able to express eventual completions of subtasks. So we want to be able to express eventually visit a subset of the accessible points of interest. And then we want the ability to be able to specify sequencing of subtasks. So visit some subset of the points of interest in some specific order. And so the benefit of sort of restricting ourselves to this more structured space is, it's human inspired, and it drastically improves our ability to efficiently infer temporal logic specifications. So in this synthetic toy example I gave you, we need maybe 4 examples to be able to infer the correct specification. In this case, the system can infer the correct specification with about 10 demonstrations. So not bad. We can look at more complex domains too. So we had a number of people come into the lab and set a dinner table according to various menus. And using a little over 70 demonstrations, we were able to infer the correct specification for setting of that dinner table. What's nice about this Bayesian approach is that we don't infer just one specification. We actually maintain a belief over the specifications for successful completion of the task, and that has benefits as well. And so one of the things that we can do is leverage the belief over specifications of the task to support flexibility in execution. LTL, even a single specification is going to give you flexibility, as has been demonstrated in prior art, Hadas-Kresge-Zeit, for example. But maintaining a belief affords you, the ability to trade off creativity versus risk aversion. You have additional knobs you can tune in the behavior of your system. And so this is giving you an example of technique we developed for planning with uncertain specifications, or with this belief over specification of the type you would get from learning from demonstration. And there are multiple potential ways to roll this out. In this case, in setting the dinner table, the only true hard ordering constraint is that the small plate needs to be placed on top of the large plate. And so when the system gets going, in this case, over off to the right, you can see we're hiding one of the April tags. So the system kind of doesn't see one of the plates, and it will continue on to set the rest of the dinner table. And finally kind of hold out when that small plate is the only feasible next step it can take to still complete the task according to the specification. And when that plate is removed and it can see it, it continues on. Okay, so this line of work, has continued on even via COVID. This is the work of a really outstanding PhD student in my lab, Ankit Shah. And the latest work is in being able to refine the delineation between acceptable and unacceptable tasks through an active learning approach, through the system exposing executions near that boundary and taking feedback from a person to further refine that boundary. And what I'd like to do is just highlight the generality of the approach. So although we demonstrated this to you in the context of these simple examples and this example of a robot setting a table, the motivation for learning LTL specifications from demonstration actually came from a project with Lockheed Martin and Air Force Research Lab, where we worked with them or the conception was, and we succeeded in developing a system that would be able to take observations of missions, large force exercise missions involving many dozens of aircraft, and be able to process those mission executions in a way that enables pilots to more quickly review those missions, to identify weak points or where tactical or mission objectives were not met. And the reason this is valuable is that today, after all these dozens of aircraft go out and fly a mission, it's a very manual process for those pilots to sit down individually and review moment by moment what happened on that mission and flag key points where something didn't go as anticipated or whether there would be room for improvement. And actually, they usually don't get very far in that process before they have to go and fly another mission. And it's that review process in a team that is critically important to improvement of a team. And so, so we worked with them to develop this, or really Lockheed developed this synthetic environment for us in which actual pilots, F-22 pilots, sort of flew these missions, a combination of actual pilots and sort of constructives. And the mission had kind of these 4 phases. You kind of push out to go to the targets of interest. There's sort of this interaction phase in which the friendly aircraft meet other entities in the environment, and then they leave the space back to their kind of safe zone. And this gives you a sense of the process that the pilots go through after a mission. There's 4 main mission objectives that they're trying to assess. And if they get as far as just assessing these 4 mission objectives, that's a big win for them. They very often don't. They're lucky if they even just figure out and come to some common understanding as to whether they met their mission objectives. But these lower level tactical objectives are the ones that they really need to be able to assess to be able to improve. Much like any team, any sports team needs to be able to assess at some granularity what happened to be able to improve. So it turns out all these mission objectives and all of these tactical objectives can be represented with LTL. So LTL is not so limiting. It's quite expressive for these real world applications. And in our project, to get to the point of being able to infer LTL, I'll just say requires a lot of work, working from the trajectories of the component aircraft to tagging the mission phases, to be able to identify and label kind of the contracts or interactions between different aircraft. But ultimately, through these processing steps, what we end up with is Booleans that specify the evolution of the state of the mission, and we aim to infer LTL. And so these are the Boolean propositions that represent the missions. And we developed models for gain and maintain air superiority, destruction of the targets, as well as levels for friendly attrition. And so I'll just show you what is learned when you look at a few dozen examples of missions and you tag them as either succeeding or failing in gaining and maintaining air superiority. What does the system learn? This is very interesting to our collaborators because they have no specific definition for what it means to gain and maintain air superiority. So this is what the system tells us it means. And I'll play one of these sort of videos so you can see why it might be easy to miss something that happens on review of one of these missions. So the system inferred that to gain and maintain air superiority, you need to never lose more than 25% friendly aircraft. You need to ensure your strikers are never shot upon and your strikers are never shot down. Eventually, you need some level of hostile attrition and you need to release your weapons, and that you need 50% hostile attrition before weapons release. And it turned out that in one of the missions, our subject matter expert actually failed to note that they had not gained and maintained air superiority. So he had missed in his own manual review that actually they did have more than 25% friendly aircraft shot down. And when the systems brought this to his note, he confirmed, oh, I missed that. Actually, I need to change the sort of label for this mission. And so, another nice thing about LTL is that it is fairly human interpretable. It's fairly easy to make sense of this, for a pilot to make sense of it and either and make modifications based on what the system learned if necessary. And so, so that is a tour through some of our lab's recent work in this sort of refined step in being able to learn from observation and demonstration and moving forward through an active process of refining both the human model, the model of the human that you're aiming to work with, as well as the task that needs to be accomplished. And so what we've also done lately is take learned models of the human, and what I'll show you are specified models of the task. So not everything is linked together yet, but specified models of the task. And automatically joining those to produce a robot model in the form of a POM-DP that can be used for a robot to then kind of play the game with a person. And I'll show you this. We worked with these a few different scenarios to exercise this capability. One is a handover scenario. So this is a case where a person comes into the lab and is tasked with preparing sandwiches at different stations. And in this case, the robot is supporting the person by providing one of the objects necessary for development of or preparation of that sandwich. And so the robot needs to predict where and when the human will be in order to successfully complete that handover. In the next scenario I'll show, we're working with a granular state space, so 2 × 10⁶ size state space, so a fairly large state space And our system is ultimately planning on a horizon of 0.3 seconds, both the action, its movement through the space, as well as I'll show you communicative actions. And the second task we worked with was a shared workspace task, where again, a person came in and was tasked with preparing sandwiches at 4 different stations. And in this case, the robot has its own independent task it's doing. It's pouring juice at the stations, and the human and robot need to share space safely and efficiently. So basically deconflict the stations they're going to be working with in space and time. And so what we were able to show with human subject experiments was that by employing the model, by employing a learning approach to the model of the human that's using constrained variational inference that I presented early on, the human robot were able to perform the task faster and with more successful handovers. And so that just gives you a sense that learning from the data from an actual human is better than an expert trying to hand code a model of a human in this context. Similarly, the video I'll show you includes planning the robot's actions, its movement through space, as well as communicative actions. And what we're able to show is that, again, with joint planning of action and communication, the team is able to complete the task faster and with more communications than you would get via a handcrafted model of communication, where you want to be conservative in how much the robot communicates because you don't want it to over communicate and bother the person. So in the video I'll show you, the person and robot are preparing sandwiches together. The state space is large, as I mentioned, and on a horizon of 0.3 seconds, the robot is choosing its next action and deciding whether to communicate on every 0.3 seconds, as well as what form of communication. So we provided a few different forms, either explicit command.
Hey teammate, let's make some meals. I will pour juice. Please make and wrap the sandwiches. Let's start. Please make the next sandwich at 2.
So in this case, the robot is highly uncertain what the person will do, and so explicitly directs the person's next step. Okay, so you see at this point, the robot is not communicating all along the way. Actually, every 0.3 seconds, the robot is not communicating. And that's because it has high confidence in where the person will be moving next. If it's in this middle region, as part of the communication policy, we provide the option for the robot to provide status updates about what it will do.
I am pouring juice at 3.
So in that case, it updated where it would go so that the person could deconflict. That it's a much more efficient and lower overhead mechanism of coordinating teams than explicit commanding. If you're ever in a team in which people are explicitly commanding each other what to do, you should exit that team.
I am pouring juice at 4. I am pouring juice at 4.
So in that case, the robot repeated that update because at the next time step, it still did not have sufficient sort of certainty as to where the person would be. But it gives you a sense of the frequency at which the robot is choosing not to communicate.
Julie?
I finished pouring juice.
Okay. So in this setting, the robot is constantly, let's say, tracking kind of an LTL description of the task and using that also for kind of forward planning and taking uncertainty into account to decide what it should do and when it should communicate with the person?
So in this case, it's not explicitly using an LTL description of the task. It's an MDP, but the LTL can be compiled to an MDP. And so while these pieces are not linked together in this demo, conceptually, the work is linked, if that's helpful. In this case, this is primarily showcasing two things. One is the model of the person was learned through constrained variational inference, and so we compared the collaboration when the model is, let's see, I think I don't have that slide for you. Here we go. So compared when the model of the human is learned through a supervised approach versus handcrafted, hard-coded, versus using constrained variational inference. And then here, the benefit of planning online the communicative actions and the benefit that has for better intermeshing the human and robots actions and improving performance of the team.
And just one more, sorry. And the MDP has state space and no certainty about what the human is gonna do next, just through the transition models then? Or is there also observational uncertainty in there somewhere?
We don't, it's just in the transition function of what the human will do. So in observation, so we are employing we are incorporating the latent state, there is uncertainty over the latent state of the human, which is in this case encoded as their intent or their priority and preference over their sequence of actions, but no observation uncertainty around where the person is in the space and the observable state space. We're using a motion capture system for that. Wonderful. So what I have done is given you a quick tour through some of the work in being able to refine plans for working for robots working with people, and then our recent work, which I'm very proud of bringing a few different pieces of work in the lab together around a system that can online collaborate with a person on an interdependent task. And we continue to push this forward. So I have agreed to, and it will be our greatest challenge, bring both the LTL work as well as the constrained variational inference, as well as other techniques we have for predicting humans' progress through the task together in a demonstration for the MIT Museum, where unlike in our factory demonstrations where we are there and supervise the robot as it is working with associates, people will be able to, thousands of people a day, I'm told, will be able to come into the MIT Museum, teach the robot tasks and work with them for this demo. So sometime in the next 2 years, come through Boston and check out this robot in the MIT Museum. And so what I want to do with maybe the last 5 minutes or so is switch gears and tell you a little bit about something different about teaching and about an effort that we have in the new MIT Schwarzman College of Computing with a focus on social and ethical responsibilities of computing, which we call CERC. So I have a role as Associate Dean of CERC within this new College of Computing. And since I have you as a captive audience, I want to tell you what we have been doing so you can help us with it. And so the College of Computing at MIT has 3 components to its mission. One is to advance computing fields, the traditional computing fields, to continue going deeper in what we already do very well, as well as advance computing across disciplines, facilitating productive collaborations between ECS and other disciplines at MIT. And then the third is to advance social and ethical responsibilities of computing. And this is the component I wanna talk a little bit about. So it's a third of the College of Computing. It's a very strong emphasis and is being treated as such. And the vision for what we're aiming to do is actively weave social, ethical, and policy considerations into the teaching, research, and implementation of computing. And trying to move forward how we prepare students as well as facilitate research to address these challenges in everything from from what we teach our students, but across design, policy, implementation, and impacts. And so the key to this is bringing multiple perspectives together. And not just putting guardrails on technology, but much as the reason I'm inspired, in the work that I do in research is also to develop technologies for human benefit and well-being. And so this component of the college has much like other academic endeavors, has a focus on teaching, research, as well as broader engagements. And in teaching, what we're aiming to do is not develop new requirements or new standalone classes, but what we're aiming to do is weave CERC into we're starting with undergrad, but nearly every undergrad class in computing at MIT, such that it's essentially inescapable for our students. So this is the way we're going about this. And to facilitate this, we're developing content, easily consumable, chunkable content that faculty can incorporate into their class in the form of peer-reviewed case studies in SERC, as well as active learning projects. So bringing, not just readings into class, but making it highly related to the technical content and the assignments, the programming assignments and the problem sets in the class. And so we undertook this effort to develop this new case studies series in which, these are 3,000 to 4,000 word articles. So really relatively short, super easy to just plop into, 1 week of one class based on empirical original research and designed for undergraduate instruction. The case study series has an editorial board made up of many, many faculty across MIT. And each submission is reviewed by a number of 4 to 6 senior researchers at MIT, not just from computing, but also across the humanities and the social sciences. And we also have undergrads that have reviewed these case studies to ensure that they're the customers, to make sure it's actually something that they can read and that works for them. It's not too deep in the discipline, but is suitable for someone without prior coursework or teaching on some of these subjects. And so I wanted to share that we have our first series of case studies published. So you can find it at MIT-Circ at .pubpub.org, published fully open access. Authors retain the rights, so scholars can use this as a part of their book, or we can work with them to extract something from a book or something from one of their related papers. Our undergrads insist and tell us each one of these is just 10 minutes of reading time, so it should be not a major burden. But we just launched the first issue, so here are our first 4 case studies. They span topics from privacy, issues related to privacy. The format changes too. So the first one on privacy is very interactive, almost like a role play you can use in your class, to a case study on who collects the data and for what purpose, and what are the factors that go into the upstream process of the data that we then work with, and how can we better understand that and what it means. Very nice case study on facial recognition technology and racial disparities, as well as one on the criminal justice system. And so please check it out. If you find a use for them in your courses, please reach out and let us know. We have a few more in the works. You can see the authors are not just from MIT. One of the authors is from MIT, but we're looking for great authors more broadly, and that are vetted through the MIT editorial board. And we have a number in the pipeline. So these will be published twice yearly, one in the winter, one in the summer. So please do check back in the summer for the next that are in the queue. And I think one of the challenging aspects of this is not just the topic, like a topic that you would want to teach in your course, but who is really like the right author for a particular topic and is willing to work in this different format for this different type of audience at this length. And so so please, if you have any suggestions, or you yourself have a suggestion for something that you would be excited to write on this, please do reach out to me personally, or you can email the suggestion box here, and we'd be delighted to work with you. And so, and then just as a thing to look forward to in the future, many of these case studies are being flowed into classes in conjunction with active learning projects. And we have a number of faculty that are working to develop new active learning projects, not necessarily linked to the case studies as well. So these are faculties drawn from across all 5 schools at MIT, working to develop new homework assignments, labs, in-class demos. Some undergrads are involved, but really the key to this is grad students that help take the ideas and turn them into something that can be piloted. And we have a number of these underway that we'll be publishing this summer, again, free and open for others to draw from. number of faculty involved. We're very excited in a new model that Leslie Cabling is actually redesigning every single lab in our very, very large undergrad machine learning class to incorporate Circ material. And so all of that is just to say, please look out, see whether these case studies will be useful for your courses. Please provide us feedback on them so that we can make them something that is more broadly accessible and usable. And please check our site for the new materials that'll be forthcoming. And so with that, I can wrap up and take any questions. Thank you so much.
Thanks a lot for the technical content and mentioning this in the end. I think this is going to be a really good resource, right, for teachers everywhere. I think having these case studies is really helpful. Any questions from the audience? Blake actually is raising his hand. Blake, go ahead, please.
Thanks, Dieter. Really interesting talk, Julie. I've been working a lot in the medical domain, and the team we're focused on is the surgical team. And there's interest in, say, a robotic assistant integrated into the surgical team. And there, the communication, it can be very command-driven. For example, the surgeon will say suction, and the assistant needs to perform suction right then, and also needs to figure out the appropriate place to perform suction. But it's not completely hierarchical because, for example, the scrub nurse is responsible for sterility and making sure that nobody accidentally breaks the sterile barrier. So do you think the LTL formulation would be flexible enough for that kind of mixed hierarchy?
Yeah, so that's a good question. So LTL, we're using it just to represent the task specification, not anything related to agents, their relationships, hierarchy, or even communication currently.
Okay, I missed that. Yeah.
Yeah. So my husband is a surgeon, so I've talked about this with him at length. And the studies that I refer to on implicit communication and coordination, they come from aviation. So they're the basis of aviation crew resource management, CRM, and then there's the military version of that as well for team training. And there is some literature in CRM for surgical teams too. And what my husband tells me is that what he said almost exactly was that a surgical assistant needs to follow the explicit commands of the surgeons, but the best ones will anticipate the needs of the surgeon. But that's not necessarily an easy thing to do. And so there's like nurse shortages, and it's much better if they've worked together.
Right.
But in many cases they're not.
For years, I've heard that too,
Yeah.
that like even a simple command, quote unquote simple, like suction, a neurosurgeon in particular told me that, getting them to understand what is meant by that command could take a year.
Yeah, yep. And then this was a long time ago, but for my PhD, I talked with a number of nurses and doctors beyond my husband when I was working on this from another angle, like not a machine learning angle. And it was fascinating because the doctors insisted, or the surgeons insisted, that over and over that they were unpredictable, like that their needs couldn't be predicted, and that they needed to ask for what they needed. But the nurses told a different story and how important it was. You're like, oh.
There were some eye rolls there.
Yeah.
Yeah, great. Thank you.
All right. I think Howard asked in the chat whether there'll be an opportunity to obtain data from the planned exhibit at MIT Museum.
Yeah. So we're setting it up as like a living laboratory type thing, like pending, the IRB approval, but it seems very, very possible. And so, and the idea is that, you know, we will always have some setup that's kind of hardened that will work for the museum goers, but then we'll have the opportunity to, you know, bring our new algorithms, our new models, and run run studies. You know, likely if we're doing something new, we'd be there. But it's a really, you know, exciting opportunity to collect data and learn from people, like longitudinally as well across people. I think opens up a lot of possibilities for future research.
Yeah, very exciting. So Julie, thank you again. So that was fascinating work, and thanks for joining us, and hope to see you soon in person.
Thank you so much. Thank you very much for having me.